Hello everyone, Mike Aben here with some more KSP math. In the previous episode, I took this little science station we have here and I worked out what its electrical needs was going to be if I put this thing into a low orbit about Kerbol. We worked out how much battery storage it was going to need and how much electrical generation it was going to need, and to be able to deal with being both in the dark and in the daylight. However, when it comes to solar generation, when we take a look over here at the side, and take a look at, for instance, here I have these gigantors, and with the gigantor it tells me that they generate 24.4 units of electric charge per second, but that is only true when we are around Kerbol at that distance from the sun. As we move further away or closer to the sun, that number is going to change, and it's going to change by a rule called the inverse square law. So that is what we're going to talk about today. We're going to talk about the inverse square law, how does it work, and to put it to the test, we're going to take this station and put it around two very different bodies. We're going to put it around Moho, our closest body to the sun, and then we're going to put it around Laythe, a moon in orbit about Joule, which is a pretty respectable distance away from the sun, and see how do we have to modify this thing to deal with both of those situations. So, without any further delay, let's do the math. Now, before we get into this any further, I do want to make a bit of a addendum, not much of a correction as much as further information. Actually, there's a better way I could have handled the science collecting when it came to this thing. Number one is I originally had 4 of these Communitron 16s on here, and I reduced it down to 1 because if we take a look at the electrical demands for the Communitron 16, it says here that the Communitron 16 requires 20 units of electric charge, so I naturally assumed that 4 of them would require 80 units of electric charge per second, and I went, oh my gosh, that's going to be expensive, let's go back down to 1. Well, it turns out it doesn't work that way. When you transmit, KSP will only ever use one antenna. It will pick what it feels is the best antenna, and that is the one it's going to use. When you start putting in more antennas, the only thing that affects is your signal strength, which you think would affect the rate at which you can transmit and therefore the amount of electricity you're going to be using, but it doesn't. Instead, signal strength only affects the amount of science you can transmit. The actual cost of transmitting in terms of time and electricity doesn't change with signal strength. So 4 antennas as far as electrical usage is just as good as 1, so I'm going to go back to my original plan and put 4 of these on here because I thought it looked better. The other thing that I did that I wasn't particularly happy with is I sat there and I said, oh wow, 20 units of electric charge. What I'll do is I'll just slap on another one of these gigantors which will cover that 20 units of electric charge, and that really wasn't a very, I think, smart idea, because you're only going to be using the 20 units of electric charge per second when you're actually in the act of transmitting. And after I posted that episode, I got and did a little bit of work, and I figured out that, you know what, you're better off just working out how much electric charge you're going to use and then figure out the battery storage you need in order to do that, and it really isn't that hard. So I'm going to pick, we want to transmit an arbitrary, let's say 250 units of science from our science station. We've done a bunch of science generation, now we're ready to transmit, and I just picked 250. It seems like a lot, probably would transmit more often than that, but yeah, it seemed like a nice number to pick. Now, if we take a look again at our Communitron, we can see its bandwidth is 3.3333 mits per second. And I know this is a bit confusing, but a mit and a science point are the same thing. So what this is really saying is it can transmit 3.3333 science points per second. And again, that's independent of what your signal strength is. So what we can do is take our 250 units of science, divide by the 3.3333 to get how much time that is going to take. And then if we look a little bit further down, we can see our electrical demands are 20 units of electric charge per second. So once we've done that dividing, we can multiply by 20, and that's how much electric charge is going to be required in order to transmit that 250 units of science, and that just turns out to be 1,500 units of electric charge. And if I add that on to what I already worked out from last episode, that this thing needed to have 3,356 in order to get through the night, all that adds up to is like about 4,800, 4,900, let's call it 5,000 electrical units of storage that this thing would require. Already right now, this big battery here is 4,000 units of electrical storage. So instead of adding on this extra solar panel, what would actually have been by far the smarter thing to do is to simply add on another 1,000 units of electrical storage. Whoops. There we go. And boom, that's it. I don't need that giant, just need a single Gigantor now. In fact, if you recall from last episode, what I actually could have gotten away with was 6 of these guys. Put that on two-way symmetry. And extend these. This would have been enough. And it would have been a significant cost savings and also a significant mass savings. And actually, frankly, I kind of like that, just like that. So now this thing, actually, I can transmit my science whenever I wanted to, as long as I made sure that I had reasonably full batteries, and this thing would actually be able to still fill the batteries up on the far side. Okay, but what I'm really interested in is what changes do I need to make if I were to put this thing around Moho or around Laythe. But in order to get to that, we need to talk about the inverse square law. My favorite thought experiment to illustrate why the inverse square law works the way that it does is to imagine a physicist with a proud new invention, the butter gun. This brilliant device will butter a slice of toast with a mere squeeze of the trigger, thus saving untold milliseconds from your morning routine. Wonderful, but I hear you thinking, I really like toast, and I would like to do more than one slice at a time. No problem. Stepping back and doubling the distance between the gun and the toast will double both the width and the height of the butter cone, enabling you to now butter 2 times 2 or 4 slices of toast at a time. This of course comes at a cost. The amount of butter dispensed by a trigger squeeze remains the same, which means each piece of toast would now receive a quarter of the butter that it did before. That is, the butter field strength would now be 1/4 of the original butter field strength. Of course, this pattern just continues for further gun-toast separations. Triple the distance, and the butter field strength will be 1/9 the original. 4 times the distance results in a field strength that is 1/16 of what it was before. And this, quite simply, is the inverse square law. Mathematically, we say that the field strength, F, is inversely proportional to the square of the separation distance r. We write it down like this, alpha being the common symbol to denote a proportionality statement. This means that the ratio of the new field strength, F2, to the old field strength, F1, is calculated by taking the ratio of the first distance, R1, to the second distance, R2, and squaring it. The inverse square law not only works when talking about light, which is how we'll be applying it, but is a common property of many fields, including gravitational and electrical ones. Let's turn this into a formula for electrical generation in KSP. We'll let an E be the electrical generation we require at some location, and E0 be the electrical generation at Kerbin. This would be the number you would see in the VAB. The ratio of E0 to E would then be this, where r is our distance from the sun and r0 is the radius of Kerbin's orbit, 1.36 times 10 to the 10 meters. A slight rearranging gets this formula. This will calculate the solar generation we'll need regardless of where we are in the system. Let's put it to the test around Moho. Now the first thing we're going to want to do now that we are around Moho is calculate how much time we're going to spend in the dark. So we need to pick ourselves an orbit. Last episode I put this into a 120 kilometer orbit about Kerbin. Let's be consistent. I'll put it in a 120 kilometer orbit around Moho. And if we pull out our formula that we developed 2 episodes ago and start to substitute in the numbers, we got to put in our radius of Moho into our formula, and if we do that, we get a time in the night of 813 seconds. let's take this back into the VAB. Now, this thing consumes, we worked this out last episode, between the lights and if it's processing science, 5.24 units of electric charge per second. So if we take that, multiply it by the 813 seconds we're going to be spending in the night side, that turns out to be 4,260, we'll call it 4,300 units of electric charge that this thing is going to use over the course of the night. Now, the other thing I need to think about is transmitting said science. Now, these 4 communitrons simply flat out are not going to reach from Moho all the way back to Kerbol. And so I got in and did a little bit of calculating, and I have a video on calculating relay strength, so I'm not going to go over all of those formulas right now, but what I determined was that with a tier 3 tracking station, that 2 of these HG-55 communitrons will service Moho very, very nicely. So we're going to stick 2 of these onto the side here. What are these? Oh, they extend that way. Don't want to interfere with our... There, put them this way. There we go. So 2 of those should service this nicely. So now let's do the same thing I did before and figure out, well, how much electricity do I need in order to transmit, again, an arbitrary 250 units of electricity. So if we take a look, or units of science. So if we take a look at the communitron HG55 and take a look over here at its bandwidth, we can see that it takes 20 MITs, or 20 science points per second. So we take our 250, divide it by 20 to get how many seconds it's going to take to transmit. Despite the fact that we have 2 antennas, it's still going to cost us 133.3 units of electric charge per second in order to transmit that. So we take our the result from the 250 divided by 20, we multiply that by 133.3 to get 1,666.25 units of electric charge to transmit that science. And if we add that on, that comes out to 5,928 units of electric charge for electrical storage that we're going to need. Let's round that up to 6,000. So we need to have 6,000 units of electric charge on this thing in order to both survive through the night and to do our transmitting. Right now I have this big 4,000 unit battery down here. I have the 1,000 unit battery up here. Well, doesn't take much to realize if I add on another 1,000 units, that's going to do the trick right there. Feels a little bit tight, so what I'm going to do, just to sort of round this off a little bit more, actually, how about these ones? Yeah, let's put on 2 of these. That's another 800. That makes me feel a little bit better. I always want to go a little bit past what I need. Okay, now, how about electrical generation? Well, remember how this works. In order to work out how much electrical generation you're going to need, you need to first of all deal with the 5.24 units of electrical usage that the science lab and these lights are going to use up. So that's number 1. We've got to add that up. On top of that, we need to recharge our batteries. And again, potentially, if we did some transmitting, we could have used up to 6,000 units of electric charge while we're on. We'd like to recharge all that. So we're going to take the 6,000 units of electric charge, and we're going to work out next how much time are we going to spend in the day. And again, to do that, we use our orbital period formula to work out the orbital period around Moho. And the orbital period around Moho turns out to be 3,444 seconds. Subtract the 813 seconds we'll be spending on the night side to realize that in the day side we are going to be 2,631 seconds in the light. So we have 2,631 seconds in which to charge up our batteries. We would like to get about 6,000 units of electrical charge going, so that means we need generation in and around 7.5 units of electric charge per second. So you might be thinking we can do that, but you know what? It gets better. We are closer to Moho, so our electrical generation will improve as we get closer to Moho by the inverse square law. So let's just pull up this formula that we created just a short while ago. Now the uppercase E is the electrical generation that we want, so 7.52 electric charge per second. The R is our distance from the sun when we are at Moho. Now Moho has an elliptical orbit, so the best plan is to take the worst case scenario. That would be that you're out at apoapsis, and Moho's apoapsis from the sun is 6.316 times 10 to the 9 meters. R0 is just Kerbin's distance from the sun, which is 1.36 times 10 to the 10 meters. We substitute that all in, and that comes out to be 1.62 electric charge per second for our E0. The E0 is the electric charge we need at Kerbin in order to get the 7.52 that we want at Moho. 1.62 electric charge per second is nothing. And if we take a look at our old friends here, the SP-L16, they are 1.6 units of electrical generation. What that means is we actually only need really almost just one of them, but in fact we could get away. 2 is ample. So with that, why don't we F12 this thing around Moho? And here we are in orbit about Moho with Kerbol large and blazing there for us. Our solar panels are nicely exposed and our batteries are completely charged up. So let's put this through the first test here. Bob is already in the science processing lab, and if we click on it, oh lordy, I happen to have exactly 250 units of science. What an amazing coincidence that happens to be. Well, let's transmit that and see if we end up using the amount of electric charge that we suspect we should be. So transmitting said science. Just to remind everyone, our calculated value was 1,500 units of electric charge this should cost. We're starting with 7150, so if we subtract that off, that should be about 5650. I don't think it quite got down that far, but I think it got pretty close. Remember, it is recharging while it's transmitting, so that might be it. And so step number 2, well, I also happen to have quite a bit of data. Another nice round number somehow, but let's start doing some research, because that will get us now using up 5 units of electric charge per second, including our lights, will get us using up our maximum electrical usage. We should be able to still survive the day. We're going to be charging up our batteries, no problem at all. Let's see how this thing does for a nighttime transit. Alright, our sun is about to set. And there we go. We are now running purely on battery power. And we should be starting to see the sun coming up in not too distant future. There it is. And without any issues whatsoever, we're charging right up again. So this thing is completely fine. In orbit about Moho now. Let's see if we can get this thing to Laythe and see what changes we need to make there. Right off the bat again, antennas. Antennas are going to be an issue. These are not going to be significant, but with a little bit of calculating and some help from our knowledge about calculating signal strength, 2 of these Communitron 88-88s work adequately, is what we will call it. Okay, so let's figure out how much electrical storage we're going to require. Well, again, we need to work out what our night side time, and since now we've used this formula a few times, I'm just going to cut straight to the chase. In a 120 kilometer circular orbit about Laythe, our time at night is going to be 654 seconds. So with that and our 5.24 units of electric charge that we use up per second, we end up with a nighttime drain of 3,427 units of charge. But we also want to think about transmitting. So once again, I'm going to pick that arbitrary 250 units of science that I would love to transmit. We're going to take a look at the Communitron 8888, and of according to this here, its bandwidth is also 20 MITs per second, or 20 science points per second. So we're going to take our 250, we're going to divide it by 20, and in order to transmit that, it takes 200 units of electric charge per second to transmit. So 250 divided by 20 times 200 gets me that that's going to cost me 2,500 units of electric charge. So I got to add that on to my storage, and if I do that, I now have 5,926, or let's call it 6,000, and lo and behold, miracle of miracles, that works out just fine, because I got 4,000 here, there's two 1,000 batteries there, plus the extra stuff that I've stuck on. I don't think I need to modify the amount of batteries this thing has at all to deal with storage, so that's great. Now let's think about generation, and this is where things are going to get a little bit tricky. If we take how much we drained during the night and how much we got from doing our transmitting, we got to replace that 6,000 units of electric charge. We're going to spend 1,536 seconds in the day. If you divide the 6,000 units of electric charge we need by that about 1,536 seconds, and also add on the 5.24 seconds of electric charge per second that we have just running the science lab and the lights, we need a generation of about 9.1 units of electric charge per second. So you might be saying to yourself, oh, well, that's not a problem. 9.1, if we get down to here and take a look, for instance, at our Gigantors, well, there are 24.4 units of electric charge just right there. But hold on, that's in around Kerbol, and now the inverse square law is going to be working against us. And in fact, if we do the work this time, we end up that we need the Kerbol equivalent of 258 electric charge per second. So we're looking at about 10 Gigantors in order to get the job done. That's getting a little bit ridiculous, right? I mean, if I started like, no, that's just way too many. So solar generation feels like, oh, that's just not going to work. Thankfully, KSP gives us an alternative. We have the PB-NUK, or the PB-NUK, the radioisotope thermoelectric generator. These things use a radioactive isotope to generate heat, which generates electricity. Not a lot, right? If we take a look here, it's 0.8 electric charge per second, but it will do that continually everywhere. It doesn't matter if it's in the light, in the dark, or whatever. And if we stick one of these on here just very temporarily, I'm not going to keep it there, you can see as well they're not that big and they're not that heavy. They're only 80 kilograms each. Now we don't have to worry about charging up our batteries from our drain during the night. We're not going to drain during the night. In fact, the only thing we have to do is make sure we provide enough to supply the needs of the ship, which is 5.24 units of electric charge per second, plus a little bit left over to recharge the batteries if we do some transmitting. And that is going to be it. So if we take the 5.24 and divide it by the 0.8, we only need 6.55, let's call 7, let's call it 8 of these things. So we need 8 of these thermonuclear electric generators. So, I mean, I could just go 8 times symmetry here. There's 8. I don't know. To me, that seems goofy. This will work, but also, although these things really don't generate radiation in the game, in real life, you don't want them right next to where people are coming in and out of a door. So why don't we instead do something a little bit different? There we go. Now they got some air around them, right? Because these fins actually, they need to, well, not air. They're going to be in space, but you know what I mean. And there we go. That should take care of all of our electrical needs. Just that right there. So once we're out in the environment of Joule and that kind of distance away, solar generation's no longer our friend. Nuclear becomes our friend. But we're not done yet. Now remember, I put on all these batteries to deal with nightside generation, or nightside electricity loss. I don't have to worry about that now with these RTGs. So the only storage that I need is for the electricity that I'll use when I'm doing some transmitting. Again, that's going to be 2,500 units of electrical storage. So that's all I need. Maybe a little bit more than that, so I don't cut it quite so fine. Let's say 3,000 units, but either way, I don't need this. Whoops. This big old one here for 4,000 units of electrical charge. I don't need that. This is here. These two here are 2,000. These are 400 each. You know what? If I just simply, let's say 3 times symmetry that's now 1,200 units, plus this, that's 3,200 units of electrical charge, plus miscellaneous elsewhere. That's going to be easy. So this should do it. So here we are around Laythe. There is the sun, nice and tiny in the background, but we aren't reliant on the sun now for our electricity needs. So let's take a look at electricity. We are fully charged batteries. Let's put it through the first test once again by transmitting away our 250 units of science. That should drain the batteries, but we should be perfectly fine. So let's transmit. Off it goes. You can see the batteries going down, but we should not run out of electricity. And as you can see, we are perfectly fine, and now it's in the process of charging up. And although the rate of charge is not great, it really doesn't matter that much, because even if we start to go into the night side, I think we might be charged up before we get there, but that's okay. But even if we did go into the night side, it wouldn't have mattered. So that is going to be it for this video. I hope that you found this useful. I hope that I solved some of your electricity needs. And in the meantime, thank you for watching, and hope to see you again next time.